Thanks for joining us on another episode of Space Nuts. Always great to have your company. And on this week's show, got a couple of asteroid stories to talk about. One that hit China about 50,000 years ago, and a potential asteroid strike on Earth. Looks like it's been averted, not due to anything we did. It just has been reported in the news as no longer going to hit Earth. So how could it be both? We'll look at that. There's a strange black hole that has been discovered that's spinning on its side. And we're going to answer some text questions today because we haven't done any for a while about the speed of light, about whether or not we're living in a simulation. That's a really good one. And when will we set foot on Mars, and could we live on Io and Titan one day? Those stories coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
My name is Andrew Dunkley, your host, and we appreciate your support. And with me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
What a surprise. It's me.
Yes. I was expecting something completely different. But...
No. One day that'll happen and you'll think, what?
I don't know about that.
Well, maybe not. Anyway, I'm here, and thank you, Andrew. Always good to be part of Space. No?
I appreciate it. Now, we've got a bit to get through, and we'll start off by talking about a couple of asteroids, one that hit the Earth about 50,000 years ago, and one that was due to hit the Earth not too long from now, but now it won't. We'll get to that. But this impact crater that they've discovered is in China. Is this only a recent discovery?
It is, yes, a couple of years ago, and I think what we're seeing now is the scientific paper that describes what has been found. It's in the journal Meteorites and Planetary Science, and so it's a really interesting one because China, until a couple of years ago, only had one known impact crater. It's called the Shuyang crater. Which was about, or still is, I should say. It is about, I think it's about 1.2 or thereabouts kilometers in diameter, maybe a little bit bigger than that. But the new one, which has been discovered in a place called Yilan, that is bigger. And in fact, it's now a record breaker because it's been dated, and this is all reported in the paper I mentioned, by carbon-14 dating of charcoal, because it would have, the impact would have burned wood, and there's actually probably formed a lake in the crater at one point as well, and there's lake sediments which have been dated as well. These in the geological record. Yep. And the suggestion is that it was formed between 46,000 and 53,000 years ago, which is about the same age as the meteor crater that you and I have both visited in Arizona, the Barringer crater. That's about 50,000 years old. But the interesting thing is that the Yilan crater, the newly discovered one, is bigger than the Arizona crater at about 1.85 kilometers in diameter, compared with about 1.2 kilometers for the meteor crater in Arizona. Yeah. And that makes it the biggest crater on Earth under 100,000 years old.
Okay, right. So there are older ones that are bigger. Is that what you're saying?
Yes, that's right. There are.
Well, the Chicxulub crater would probably count.
Yeah, it would count. And you sort of, in a sense, that's a good. It's worth an interesting statistic, because the further back in time we go, the bigger the objects we expect to find still roaming around the solar system in a wanton and uncontrolled way. Even though 100,000 years is not long compared with the 4.6 billion years age of the Earth. But as time progresses, you get fewer large bodies. And of course, now we're in this situation where bodies greater than a kilometre, pretty well all of them, I think it's a 90% completeness, have been discovered when you do the statistics. So, rather interesting. What would have formed it? Probably an object, probably not that much bigger than the thing that exploded over Tunguska back in 1908, but more solid. It's thought to have been probably an iron meteorite or an iron asteroid, which means it's a part of the chunk of the core of a protoplanet, a planet that was in the process of forming. Because all the iron sinks to the middle, and so you get these iron asteroids and iron meteorites that actually are the remnants of the cores of planets that have been banged into by other things, or planetesimals is actually the correct term. These small objects, protoplanets is what they grow into. Planetesimals are the size of a large asteroid, but they're big enough to have differentiated. That's to say the iron has sunk to the middle under its own gravity. So it's been hot enough for that iron to flow, and big enough to be differentiated. So what we think this might have been is the remnants of one of those. There is evidence from the bottom of the crater that it was indeed an impact crater rather than something volcanic. There's shocked quartz, which is spoken about a lot in impact circles. This is quartz that's basically been shocked by the temperature of the impact. There's melted granite. There's actually volcanic glass, or when you get high enough temperatures with rock, with silicates, you form glass. But it's got holes in it which would have had gas bubbles in, and lots of other symptoms of an impact. And it's actually worth following up on the web if our listeners care to do that, because there's some rather nice aerial photography. It's actually Landsat photography, I think, showing this crater looking exactly like an impact crater. It's in the hills in farming country. It's a sort of mountain range, and it's incomplete. The southeastern quadrant is missing. It's not clear why that should be, whether it's by erosion or some sort of asymmetry in the formation of the crater. But very interesting discovery. And as I said, it's worth looking up the Landsat images because it's very crater-like. It's just a circular feature.
If you do a search for young impact crater China, you'll probably find it. It's on the SciTech Daily website. A great story about it there. I was wondering, Fred, what China might have been like 50,000 years ago. I'm guessing there would have only been 500 million people. I don't know.
It would have been very sparsely populated, I think. I mean, China's a very big country. It's got a large land area. And yes, the climate would have certainly been different, because we know that since then there's been at least one ice age and possibly more. A different sort of place. One little detail that I really liked, it's apparently in really heavily forested country, and that might be why it's not really been recognized. Apparently it's the autumnal foliage on the trees that make it show up and in the Landsat image. But it's got a name, a local name, which I'm going to mispronounce probably, Kwanshan. And apparently that translates as circular mountain ridge. So the locals knew it as a circular feature.
I'm guessing they probably didn't realise what it was. By.
That's right.
You mentioned the comparison to the size of the object with Tunguska, but I remember us recently talking about Tunguska possibly being a planet grazer. It didn't actually hit the ground at all. So.
That's right.
But this one did. Obviously, it was an impact crater. But Tunguska was something that exploded or grazed the Earth.
Yes,
and hit it directly.
A detonation in the atmosphere, which this might have done as well. It may well have burned up some of its material in the atmosphere. but certainly was big enough to cause a crater on Earth. And that would have been locally pretty devastating. There would have been effects. There would have been a lot of material thrown up into the atmosphere. So there would have been possibly a bit of temperature change in the area.
Yep.
Maybe global effects, like we've seen curious atmospheric phenomena because of the Tonga volcano putting aerosols and dust into the atmosphere. Been a lot of really unusual sunsets and things like that, which I think are still going on. I don't know. I haven't seen a sunset for about 3 weeks because of the cloud that we've got here.
Yes, well, we've had plenty of cloudy days in recent weeks as well. It's been a very unusual summer for us, much cooler than normal. We've had temperatures out here that have just barely scraped into the low 30s when we're normally pushing towards 40 this time of year. It's a very, very mild summer, which correlates with a heck of a lot of rain. And we've seen all those floods up north of where I am, about 6 hours drive from where I am, around northeastern New South Wales and southeast Queensland. That's just a horrible tragedy with so much floodwater. And places like Lismore, for example, where I lived for a short time, worked on the local radio station there, 2LM, for a while, and they've had a record-breaking flood. They haven't had a flood that big since records began. It's just been incredible what's been happening. I did ask a few people overseas what they thought of the floods, and they went, "What floods?" All that's on in the news in other countries is Ukraine, for obvious reasons. But the floods have barely rated a mention outside of Australia, from what I understand. But yeah, it's been pretty horrendous here for a lot of people, and it's not over yet. There's a big East Coast low coming in on you, Fred, isn't there?
That's right. Yes, I'm keeping an eye on the rain radar. I nipped out just a minute ago to clear gum nuts off one of our drains that blocks the drain up.
Yeah, they do, don't they?
Floods our back path. So yeah.
Okay, well, let's continue on with our discussion about asteroids, because we've talked about a couple of strikes in recent times on Earth, and there was one particular asteroid that was in the news only in the last week or so, 2022 AE1, which they thought would impact Earth sometime in the middle of next year. And now all of a sudden it won't. And of course, the popular press is jumping all over this and saying, "Oh gosh, it moved. What happened? How did that, don't they move in a straight line?" No, they don't. But this is an unusual case.
It is a little bit, yeah. So this was discovered on the 7th of January. You're quite right. It was 2022 AE1. And the thing about discovering asteroids, Andrew, is that what you're looking at, all you're seeing is a dot of light. So just taking one image of the sky doesn't reveal an asteroid. But if you take two and you detect an object that's moving between the two images, maybe if they're an hour apart or a few minutes apart or something like that, you'll get movement in it. And that tells you that it's a nearby object, that it's an asteroid. But you need 3 observations to get a first approximation of its orbit. And that's what happened. There were 3 observations made. An orbit was calculated. This is all done automatically now. There's a thing called the Asteroid Orbit Determination Automatic System, which is, basically it's actually part of ESA's Near Earth Object Coordination Center. So it all happens automatically, and it flags the asteroid as having a risk on one or both of the 2 scales that we measure asteroid risk, the Torino scale and the Palermo scale. Both of them are, what they do is they rank collision probability with size, the amount of energy that this thing's going to deliver, and essentially give you a score. So this got flagged on the Palermo scale because those first observations indicated, if I remember rightly, it was going to be the 4th of July when it was going to be.
I think that was right. 2023. Yeah.
And so more observations were made in subsequent nights, but then the thing got too near to the moon to observe, so it was sort of drowned out by the moon. And at that stage, it was still an object of interest. It was still something that had a chance of hitting the Earth in 2023. It was the 12th to the 19th of January when the object couldn't be seen because the moon was too bright and too near to it. So they got further observations after that. I can't remember whether it was the 20th of January. It's thereabouts. And that next observation immediately ruled out the possibility of a collision. And so what's happening here, Andrew, is that it's all about how much of what we call the arc, how much of an orbit you can observe. And if you've got just a short chunk like the amount of an orbit that an asteroid covers in one night, you can get a deduction of what its orbit is, but it's got huge uncertainties.
Yeah.
Because you're only observing over a very tiny arc of the orbit. And as you progress, you track the object over subsequent nights, you can actually refine the orbit, and those probabilities come down. Those uncertainties in where it will be down the track are reduced. And that's why when it was observed over a long enough arc after the full moon period, it was immediately obvious that this was not going to collide with the Earth, because the probability shrinks enough that the uncertainty in the measurement shrinks enough that it tells you that there won't be a collision.
Yeah, it's going to miss us by a few million.
It's 10 million kilometers.
10 million kilometers, yeah.
I'm
fascinated by the Torino scale. It looks like a risk matrix that you do.
It is.
Like when I worked for the ABC, we used to have to do risk matrix assessments before we did outside broadcast to decide whether or not it was too dangerous. But this one, it gives you the size of the object and the collision probability and the ultimate effect if it does hit. So a 5 kilometer object with a certain collision probability would have a global effect.
It would.
And it goes down. This one, they reckon, would have been a localized effect.
That's right, yeah. Once again, an object actually probably similar in size to maybe the Chelyabinsk impactor, the one that exploded over Russia back in 2014.
So that rates an 8 on the Torino scale.
Yeah.
Yeah, that's still way up there. It prompts me to ask another question about asteroids and their impacts on Earth. Are there certain parts of the planet that can't get hit because of the way the angles work, or is everything exposed?
It's a good question, actually. Yes, everything is exposed because whilst asteroids, I guess if you think of asteroids mostly being in the plane of the solar system, then as you get nearer the poles, your probability is reduced. Although it's still possible for impacts to happen near the poles. But in fact, with asteroids, their orbital inclination ranges over quite a high level. They are concentrated to the plane of the solar system, but there's some that come in at quite high angles. And, the Earth's just doesn't matter which direction you're coming in from, the Earth's the same target. And if they're coming in over the pole, then, you can get them near the poles as well.
Interesting. Just wondered about that. Okay.
Yeah.
Now, if you want to find out more about this near miss that's no longer a near miss, or the near hit that's no longer a near hit, about 2022 AE1, there's a great story about it on the phys.org website, phys.org. This is Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, if you want to help us out on Space Nuts, but you don't want to kick the can for, a monthly contribution as a patron, although that is certainly something that is most welcome as well, you can do a review. Now, I don't know which podcast distributor you use. There are many, and we're on all of them. But if you like the program and want to leave a review, that would be greatly appreciated. The more reviews that we get, the more attention we get, and the higher up in the rankings we go, and the more people that listen, and that increases our community and makes for a lot more fun and enjoyment. And it helps out a lot. So if you'd like to leave a review on your favorite podcast distributor, that would be that will be fabulous. So we'll leave that one with you. And if you are interested in becoming a patron, jump on our website, spacenutspodcast.com or spacenuts.io. Now, Fred, this is a rather interesting black hole story, and this one's a little bit different because they're describing this in the Sci-Tech Daily website as a death spiral. This is a black hole that's sort of rotating flat on its back, like Uranus, I guess.
It's a bit, yes, that's right. It's not quite as acute as Uranus is, but it's definitely well tilted over. So this is research that's come from scientists actually in a place where I visited. I've may even have met some of the scientists in question up in Finland, the University of Turku in Finland, and their Tuola Observatory, which is, a lovely spot outside Turku. That's where these researchers are based, but they've used a telescope in La Palma that I'm also familiar with, the Nordic Optical Telescope, operated by the Finns and the Danes. We always used to joke about. I used to work quite a lot in La Palma in the Canary Islands, and watch the Nordic Optical Telescope being built back in the 90s. It was always a joke that its acronym is NOT. So this was not the telescope. It's the Nordic Optical Telescope, the NOT. Does great stuff, though. Great work. If I remember rightly, it's about a 3.5 meter, I think. Is that
right?
Something like that.
Anyway. You said you saw it being built in the 90s.
Yeah.
The 1890s? What was?
Thanks, Andrew. That was wide open for that one, wasn't it? Yes, it was the 1890s. That's right. Actually, you've taken me straight back to it. It wasn't quite the 1890s. It was a bit earlier than that. But that was where Charles Piazzi Smythe, who was eventually the Astronomer Royal for Scotland, did his first work on determining that mountains are great places to build observatories, and he did it in the Canary Islands.
There you are.
Not on La Palma, but on Tenerife, and he hauled his gear up to Teide, which is the volcanic peak on Tenerife, and determined that the exquisite viewing that you get from those heights is well worth the trouble.
There you go.
And of course, that was the start of mountain astronomy. It was a bit before the 1890s. There you go. There's a digression.
How about that?
Yeah. But to the story. So what we've got, and this was discovered by X-ray astronomers. I think the follow-up work was done with the Nordic Optical Telescope. It's an object called, wait for it, Maxi J1820 plus 070, and it's an X-ray source. And what we have is a binary pair with a massive star in orbit around a black hole. And the star is close enough that material is leaching from the star into the black hole's accretion disk. So you've got this star in orbit around the black hole, a disk of material which is rapidly spinning, highly energetic. That's where the X-rays come from. And it's the stuff swirling down the plug hole before it gets swallowed up by the black hole.
Yeah.
So that's a fairly standard scenario. We see that very frequently. But what's not standard is that, like many black holes, this one squirts out material from its poles. And that's material that has been kind of grabbed by the magnetic fields of the black hole from the accretion disk and sent out, usually at right angles to the accretion disk. So it's coming out, along the axis of rotation. And it is indeed the axis of rotation of the black hole. We talked about this last week. How can something with 0 dimensions have an axis of rotation? Well, it does. But in this case, the stuff is being squirted out, yes, in form of jets of material, which once again can be detected by X-rays and radio telescopes too. But the jet is tilted over at more than 40 degrees to the perpendicular to the accretion disk. And that is bizarre. In fact, it's the first time that has ever been seen.
And the obvious question is, why do we think it's doing that?
Yeah. So, as the mentioned Sci-Tech Daily, as the article says, The finding challenges current theoretical models of black hole formation. There you are. That's it in a nutshell. The theory at the moment struggles to allow something like this. I think it's the lead author he's made a comment about this. He's got a lovely Finnish name, Juri Putanen. And he's a professor of astronomy in Turku University. And he says the difference of more than 40 degrees between the orbital axis and the black hole spin was completely unexpected. Scientists have often assumed this distance to be very small when they've modeled the behavior of matter in a curved space-time around a black hole. The current models are already really complex, and the new findings force us to add a new dimension to them. In other words, I think the theoreticians are struggling to make this fit the normal paradigm for how black holes form and how they behave when they're formed. It's such an extraordinary and unexpected result.
Indeed. And you couldn't sort of simply say, well, something must have knocked it over, because it's a black hole. I mean, it's not that simple.
Yeah, that's right. It's not that simple. It sort of makes you wonder whether it's I don't know. No, that doesn't fit either. I was just going to theorize that the accretion disk has slipped. But of course, the accretion disk, the plane of the accretion disk is the same plane in which the companion star orbits. Yeah. Because it's feeding material onto the accretion disk. So that doesn't fit the picture either. I think it's the black hole that's been knocked over, Andrew. I think you've got it in a nutshell there, but I don't know how it's been done.
No, maybe another black hole.
It could just be the way it's formed, some really peculiar phenomenon when the black hole has collapsed from the nucleus of a star at the end of its life.
Maybe there was some kind of disturbance at the moment of formation.
Could be.
I don't know.
Who knows what it might have been?
Yeah, but it's fascinating, and you can go to the SciTech Daily website and read all about it. It's a great little animation there showing what's happening as well. That wraps that up, Fred. Thank you so much.
It's a great pleasure, Andrew. Always good to talk, and we'll speak again soon.
We will indeed. Professor Fred Watson, astronomer at large, part of the team here, and thanks to Hugh in the studio, who does all the not-so-essential and non-hard work to put it all together. Thanks, Hugh. And from me, Andrew Dunkley, thanks for your company again. We'll catch you on the very next episode of Space Nuts. Bye-bye.
15 seconds. Guidance is internal. 15 seconds.
That would be wrong. Where's the end? There it is.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.